So, enzyme. By the end of the at the end of this class, we will know what an enzyme is, the active site theory, enzyme kinetics, enzymes in chemical reactions, or clinical diagnosis. Okay, so let's proceed. So this is the structure of an enzyme. So enzymes are proteins that increase the rate of reaction, and they do this by lowering the energy of activation, or the activation energy. And the orderly course of metabolic processes is possible. Can you see my slides?
Yes, sir.
The orderly course of metabolic processes is only possible because each cell is equipped with its own genetically determined set of enzymes. So meaning that every cell or organ in the body has its own genetically determined set of enzymes. So there are some enzymes in the eye, some enzymes in the heart, some enzymes in the kidney, and some enzymes in the liver, which are different from other places. It is only this that allows coordinated sequences of reactions or metabolic pathways. Enzymes catalyze nearly all chemical reactions taking place in the cells of our bodies. Okay, so I will explain with diagrams. So enzymes also play an important role in a number of fields. For instance, in genetic diseases, when we are diagnosing genetic diseases, or genetic diseases have frequency or high frequency of what? Enzyme defects. Either the enzyme level is decreased or enzyme level is increased. We also have myocardial infarction, that is any heart disease. Enzymes can be used therapeutically. Whenever you hear therapeutically, it means what? Medicinal or treatment. So enzymes can be used to cure diseases. For instance, in digestive enzymes, we also have monoamine oxidase inhibitors. We will come to that. Enzymes are also used in food processing and in the chemical industry. In food processing, for instance, when we are brewing beer, we use Saccharomyces cerevisiae. Saccharomyces cerevisiae. Then the bread, fermentation, when you are producing bread, we use what? What do we use for bread? We use yeast. In the chemical industry, enzyme inhibitors are a foundation of biological weapons. So we also use them in making biological weapons, like COVID-19. That virus that people were, it was killing people. It's a weapon. Somebody engineered it. But this is a political speech. Let me not go there. Okay, can you all see this slide?
Yes, sir.
Okay, so the slide is showing a graph comprising of two curves. One, the red curve is for enzyme catalyzed reactions, and the black curve is for uncatalyzed reactions or a non-enzyme catalyzed reaction. So you can see that the vertical axis has free energy. Then the horizontal axis is the progression of the reaction, or the time it takes for the reaction to proceed, or the rate. Okay, so these are the reactants. For every reaction we need reactants, then products are formed after the reactants react or they collide to form products. This is this red curve is the course of enzyme reactions. So we can see that for the non-enzyme catalyzed reaction, this is the energy change or energy of activation. Then for the enzyme catalyzed reaction, this is what? The energy of activation. So of these two energies, which one is bigger? The energy of activation for the non-enzyme catalyzed reaction is black, and that for the enzyme catalyzed reaction is red. Which one is bigger than the other? Lar Edward.
The black one.
The black one is bigger. Very good, Annabelle. The black one. So why is it that the black one is bigger? Because you see, when this non-enzyme catalyzed reaction is proceeding without any, in the industry has what? Chemical catalysts. And in the biological systems too, there is what? Biological catalyst, which is the enzyme. So for instance, if you are mixing magnesium chloride with hydrochloric acid, you need a chemical catalyst. But the chemical catalyst is not as effective as the biological catalyst. Because the biological catalyst, which is an enzyme, has a faster rate or conducts the reaction in a faster rate. Much more better. So for instance, the same reaction, magnesium chloride and hydrochloric acid, when you are mixing them together, or in industry, when you are mixing something to generate something, some of the time it can take you about 7 days. But when you use an enzyme, that same thing that took you 7 days will now only take you about 30 minutes. So that is why God is so wise that He put enzymes in our body, so that if you take any medicine, the enzymes in your liver, which are called cytochrome P450 mixed oxidase. Let me write it on the board so that Lucilla will understand. Please off your audio, please. Off your audio. So hello. Off your audio. Cytochrome. Oh, whose audio is disturbing the recording? Annabelle. Hello. Oh, is it the policeman? Is it Sibdo Adams? I will take the person off. Can you hear me now? Okay, so this is the enzyme in the liver. Can you see it?
Yes, sir.
Okay, so this is the enzyme in the liver that metabolizes or catalyzes drugs when you take in medicine. This is what breaks down the drugs to the inactive form so that it will be excreted. If your liver is spoiled, these enzymes will be spoiled. So you can, when you take drug, it will not work. Okay, so let's go back to our slides. Okay, so you see, so what in a nutshell, when you take a drug, it's not, for example, your head is aching or you have diarrhea. Then you take a medicine and the medicine will take about 10 hours for you to be fine. Won't you be dead by then? You will be dead. But if enzymes are in your body, you take the medicine within the next 10 minutes, 15 minutes, the medicine has started working. Because the enzymes in the body are breaking down the medicine to release the active ingredients to help remove the pains or the infection that you are encountering. So that is the essence of enzymes. Without enzymes, you need a very big energy of activation. Without enzymes, please, it seems the time is, this thing is disturbing me. Hello?
Hi.
So I will lock you. We'll use the same code it has run out, so we'll use the same code.
Okay, sir.
So when you see that it has gone out, we use the same code. Okay, so you see, so you can see now,
Yes, sir.
Okay, so let's proceed. So you can see that the non-enzyme catalyzed reaction, it needs a very big energy of activation, whereas the enzyme catalyzed reaction requires very small energy. So you can see, look at this from here. But if there was no enzyme, the reaction would take place, travel here and come down before it formed the products. So an example, this is a schematic example of it. If you have lactose it comprises of glucose and galactose. So if lactose is here, you will see that this man is pushing to get here to break down the lactose to glucose and galactose. But if you have an enzyme, look at the enzyme. The enzyme is this, lactase. So when you put lactase, add it to lactose, it will quickly, you see the lactose will now occupy the active site of the enzyme. Then it will now break down the bond. It will break this bond into what? Glucose and galactose. So you see that this man is comfortably walking on what? A bare, almost bare ground. But if there was no enzyme, you need a lot of energy to climb a very big mountain. But in the presence of enzyme, oh, you need a very small energy. So God is very wise. So what is an active site of an enzyme? The active site of an enzyme is the place of the enzymatic protein which binds with the substrate. So this is the active site. This is the active site. So it has what? Backbone, environmental groups, binding groups, catalytic groups. So the catalytic groups, binding groups, environmental groups, they are all occupying the active site. So what is a protein? Last time we looked at a protein, so I will not explain this, because you can see the peptide bonds here, peptide bonds. So active site of enzymes, we have the peptide axis or backbone. and this is formed by the monotonous part of the polypeptide structure, whose folds and folds contribute significantly to the three-dimensional shape of the active site. So we are just looking at the three-dimensional shape of the active site. All this blah 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 big English that I was reading is just describing the active site. So in the active site, we have environmental groups also, which are side chains of apolar amino acids. So we have a lot of all this in the active site. Then fixation or binding groups are also located in the active site, so you read about it. And active site of enzymes. So let's look at the active site proper. Are side chains of amino acids that participate in the structure of the active site, active center, but are those that are directly involved in the transformation of the substrate. So let me share a whiteboard. So if you have a whiteboard, so let's look at this. Let's have this is an enzyme. This is an enzyme. So, and this is a substrate. So let's see, this beautiful object is a substrate. Let me sketch it well. This is a substrate. So if you bind them together, in a nutshell, we are going to have so this is the active site. This whole pocket is the active site, and the substrate is this. So let me write substrate. Are you with me? Are you all with me? Eh? Are you with me?
Yes, sir.
So this is the active site. So this is a substrate. This is the enzyme. So, oh, sorry. Where's the eraser? My eraser. Okay, yes. So, yay, eraser. Okay, I finished. So, when the enzyme and the substrate they bind together, they form a complex, and the complex they will be forming is called enzyme substrate complex. So this is the substrate. It will occupy the active site of the enzyme. So you can see the substrate is now inside. Do you understand?
Yes, sir.
So this structure is called ES complex. ES complex. ES complex. ES complex. So we are on slide 14. So the active site contains amino acids, and the side chains of those amino acids are those that catalyze the reactions. The side chains of those amino acids are those that the side chains of amino acids, they bind to the substrate, and when they bind to the substrate, it ends up what? In a reaction that will lead to what? The product formation. That will lead to the product formation. Okay, so let's continue. So you read on this. Okay, so let's look at the mechanism of action. So this is the active enzyme. This is the substrate. The substrates are two, red and yellow. So this is what's going to happen. Red and yellow substrate. So the red substrate will bind over here. The yellow one will also bind over here. You can see that the red one has this pointed side that can easily fit here. The yellow one has this side that can easily fit in this cleft. So when they fit, they form the enzyme substrate complex. Then this substrate, red and yellow, will be reacted with the active side, because it's this whole thing, the hole over here and the hole over here, that's the active side of the enzyme. So there will be reaction. The enzymes amino acid side chains over there will be reacting with the product, with the substrate, to form what? This product. To form this product. Then, please, who is disturbing over there? Bernice, off your mic. Okay, that's right. So there will be a product to be formed, the yellow color product to be formed, which looks like an orange. Then the enzyme, enzymes are not used up in a reaction. No. They are not consumed in a reaction. So the enzyme will catalyze this product, will convert this substrate into this product. Then later it will come out of the solution and go and bind to more substrate, convert them to this product. Then it will go back again to bind to another one, convert. So the enzyme itself is not used up in the reaction. It just converts the substrate to the product, but it remains the same. So we have the lock and key model. Lock and key model. Please let me sack this dog and I'm coming. So let's resume. Okay, so the lock and key model. The lock is like your door lock. If you have your door lock, you use a particular key to lock your door. So look at this. This is the active site of the enzyme, and this is the whole enzyme. So this is the substrate. You can see that the structure of the substrate can adequately fit this active site. Hey, the dog pass to the ye. Me pamucho me bawai. I beg you. Okay, so see, we have the lock and key model. You understand? The lock and key is like your door lock and your key. If the key is not meant for that particular door and you use it, it will not open. Will it open?
No.
It will not open. Last time I was reading something on the net. One lady was doing a video, and he said, some of the guys, they will go and take in some medicine so that their manhood will be very big. So if your manhood is very big and the woman's own is very small, can you make love to her?
Yeah, I don't think.
So when you are doing something, use your mind, because the thing is small and you are going to take some aphrodisiac and the thing has become so big it cannot enter. So now you'll be looking for women to sleep if you can't get, because every woman will be afraid of you. That is lock and key model. Okay, so let's go to the next model, the induced fit model. With this induced fit model, we have this is the enzyme, but you can see that the active site, the shape of the active site is different from the shape of the substrate. A substrate is what? The reactant. So you can see that it's different. The substrate is different from the shape of the substrate is different from the shape of the active site. So, but you realize that when the substrate comes into the proximity of the active site and binds to the active site, then this enzyme will compromise. This enzyme will compromise and join. It's like this man, this substrate. The substrate does not have money, and this substrate has seen a very fat lady, beautiful, curvy lady, contour lines, and you want to marry her. But you can see over here that the substrate over here is a poor man. And the enzyme, this lady, she has a car, she has everything, and she's beautiful too. But she has waited to have a husband, the husband is not coming. So now she tells herself that whatever will come, I will accept. So this poor man, substrate, ugly man will come and bond over here, and the enzyme will do it too, and we get this enzyme substrate complex. So we call this model an induced fit model. Induce what? Induce what? Okay. So we look at enzyme specificity. You see, enzymes are specific for the substrate that they catalyze. Some enzymes catalyze a single substrate. Other enzymes also catalyze several different similar substrates. Some enzymes catalyze particular type of bond. So let's look at them. For absolute specificity, we see that when we say absolute, is what? 100%. Total. For absolute specificity, we see that the enzyme catalyzes one type of reaction. We see that the enzyme catalyzes one type of reaction for a single substrate. So, for instance, if you have urease is an enzyme. It catalyzes only the hydrolysis of what? Urea. Hydrolysis is what? Using water to break down a molecule or a compound. So urease uses water to break down urea. So it's only urease acts only on urea. So it has a single substrate, which is urea. Then we have some enzymes catalyze different substrates. For instance, hexokinase can add phosphate group to any 6-carbon sugar. So you can add phosphate group to glucose, which is a 6-carbon sugar. You can add phosphate group to galactose, which is also a 6-carbon sugar. Let's also go to linkage. When we say linkage, is what? Bond or bonding. Some enzymes catalyze the breakage of specific bonds in a chemical reaction. For instance, chymotrypsin, which is found in the pancreas, catalyzes the hydrolysis of peptide bonds. So chymotrypsin is for what? is an enzyme that digests proteins. So enzymes are classified into 6 groups. We have the oxidoreductases. They catalyze, they use what? Or their reactions that they catalyze are called oxidation reduction reactions. Transferases transfer groups of atoms from one substrate to another. Hydrolases, they use water to hydrolyze compounds. Lyases add atoms or remove atoms from a double bond. Isomerases, isomerase is what? Rearrangement of atoms. And ligases use ATP to combine molecules. So let me, because of time, let me explain the last two. Isomerase, let's go to our whiteboard. So isomerase, for instance, if you have something like this, hello,
Alright.
if you have something like this, wow, this is not part. So this is CH2. Okay, so let's see. So let's see, this one will produce what? So when we isomerize this, we'll have OH CH3 Okay, so Swale, what have we done to this compound? Swale, policeman, where is he? Prosper. Prosper. Hello. Prosper. Prosper, what have we done? Prosper.
Sir,
What have we done?
isomerism.
Isomerism. So explain isomerism. The structure I've drawn there, what have I done? Prosper, me, hurry up.
Then,
Mm-hmm.
there is a thing down. Upon this our destination.
Oh no. You see, we have just done a rearrangement. We have brought this OH. It was at the right hand. It was at the left hand side. We have now brought it to the right hand side. Isn't this? It was here. Now we have brought it here.
Okay, sir.
So it's molecular rearrangement. That is what we have done. So this is called isomerization.
Isomerization.
Any rearrangement is called isomerization. Isomerism. Okay, so let's go to the next one. This one you should understand. Ligase. It uses ATP to combine molecules. Like you are combining two glucose, you need ATP to provide the energy. Anytime you hear ATP, ATP means what? High energy phosphate. So we have types of high energy phosphates. One is we have GTP. We have GTP, it's a high energy phosphate. We have cytidine triphosphate. We have this one is guanosyl triphosphate, cytidine triphosphate. We have ATP, adenosine triphosphate. Then we have UTP, which is called uridyl triphosphate. Then we have hello.
Hi, sir.
So these are energy compounds, high energy compounds. So if the cell needs energy, then GTP is what is there, or ATP is what is there. GTP or ATP GTP will be broken down to what? GMP. That is guanosyl monophosphate. It will be broken down to GMP and a pyrophosphate. This one is called inorganic phosphate, and the inorganic phosphate is also called pyrophosphate. Pyrophosphate. ATP will be broken down to what? AMP plus pyrophosphate or inorganic phosphate. Do you understand? Pyro over here means two. Two. Okay, so let's go back to our slides. Time is approaching, we have to do it fast then. So let's see. So enzyme kinetics is the science that describes the properties of chemical reaction, including those mediated by enzymes. An enzyme kinetic measures the concentration of substrates or products of a reaction to determine the velocity of the reaction. It also measures the effect of concentration, temperature, pH, etc. to characterize the properties of the enzyme catalyzing reaction. So we employ the Michaelis-Menten equation. This is Michaelis. He is a biochemist. Hello. Hello.